Okay, so this new unit is on systems of equations and systems of inequalities. And the idea is that you really need to understand how to graph a line in order, and really what does it mean when you have a graphed line, okay? And just for a quick reminder, if you have a line that looks like this, then what you've got here is an infinite series of points, each point having a set of coordinates in x and y, and whatever the equation is, this particular x comma y, if you replaced x with the coordinate from that point and y with the y coordinate from that point, it would solve it to be a true statement. It would work out equal on both sides. You could move to any other point on the line, even if it's decimals, and you could plug in the x coordinate wherever x is in the equation and the y coordinate wherever y is in the equation, and it will work out to be true. Okay, and you can do that for every single point that's on the line. So every different x and y for all of these points is a different x and y pair of values that will solve the equation. Okay, that's the first thing that you need to understand. Now, if you have two lines, there's only going to be one place where they cross, and since you have all of the solutions of the red equation here and all of the solutions of the blue equation here, the place where they meet, that one point where they meet, the coordinates of that point will be the x and y value that will solve both equations. And in this particular case, they only cross in one place, so there's only going to be one value of x and one value of y that you can plug into the first equation to solve it, and you plug those same values into the second, and it will also solve it. Okay? Any other point along this line, if you take the coordinates of, let's say, this point, and you plug it into the red equation, it'll work out to be true, equal on both sides. But if you plug those coordinates into the blue equation, because that point is not on the blue line, it will work out to be a false statement. It will not be equal, and it will not be a solution to that equation. So we need to consider that a line is just a whole bunch of different points, and each one of those points has coordinates, and the coordinates are values for x and y, a value for x and a value for y, that you can plug into the matching equation and it will solve it to be true. This is something that's a review that you should already understand. Now, there are a couple of special cases that you're going to come across, like this. One of the lines looks like that, and the other line looks like that, essentially parallel to it, or it is parallel to it, and they cross nowhere, so there's going to be no point that will solve both of them. There's no solution to the system because they don't ever cross. So that's one idea. You could also have this going on where you have both lines essentially crossing at all points. This red line and this blue line are right on top of each other. And every point that solves one solves the other. So there's an infinite number of solutions for two equations that are right on top of each other like that. Okay? Those are the big ideas. But the first thing is that you need to understand how to graph lines. You need to understand what does it mean to be the graph of an equation, right? So if you don't understand some of the stuff from Unit 5 that we covered, you should go back and review it till you get your mind around it. Sorry about the sound on the last slide. I didn't have my headphones hooked up. Now, what is the solution of the system? Use a graph. Now, right away, when I look at this, I can see that these lines have different slopes. They're in slope-intercept form, and they have different slopes, okay? So the only two special cases where they're parallel, they'd have the same slope, but different intercepts, or the exact same line, they'd have the same slope and the same intercept, tells me that if they have different slopes, I know that they're going to be doing something where they cross once somewhere, okay? But what is the solution of this, okay? Now, the solution of the system, a line represents the solutions of one linear equation. The intersection point is the solution of both equations. So when they say what is the solution of the system, what they mean is what point solves both of these simultaneously, okay? So what do? We graph both equations in the same coordinate plane, and when you do that, it looks like this, and we know how to graph in slope-intercept form, okay? It might not always be in slope-intercept form, but I will talk in a bit about what if it's not? How would you graph it? Because there's a lot of easy ways to graph lines, even if they're not. But we graph both lines, and we say find the point of intersection, and when we do that, it appears to be 2, 4. So what we know is that x is 2, y is 4, which means in each equation, and you're going to check both of them to see that it's true, you put 2 in for x, 4 in for y. That works out to be true for that one. We put 2 in for x here, 4 in for y here, works out to be true for that one. So that is the solution of the system, and the way that we say it then is just the solution of the system is 2, 4. Okay? So what is the solution of this system of equations? Use a graph. This is where you need to have graph paper in order to be answering your questions, and you can't get away without having it. So get yourself some graph paper. At the very least right now, print some out, but that's a terrible way to do it long term. So you need to just have someone buy you graph paper or go buy it yourself. Okay. Anyway, graph these, see what the solution is, and then we'll check them. All right, so what I did here is I graphed these two lines, one in red, one in blue, and I just put an arrow, but maybe I'll circle it. That's the red equation, and this is the blue equation. And what you see is then they cross right here at this point, which is -2, 0. Okay, that point of intersection. That is the solution, but we need to check it just to be sure. So I take the two equations, the red equation, I plug in 0 for y, -2 for x, and it works out to be true. You see the check mark next to it indicating that, yep, that's a true statement. And I do it again with the blue equation, plug in 0 for y, -2 for x, also works out to be a true statement. That's how we solve it, by graphing, okay? You look for the point of intersection. The trick is you need to, one, know how to graph accurately, and one good bit of this is that, excuse me, just something to indicate is that, okay, we know what the intersection is here. For the red one, it's +4. But what I did is I rise 2, run 1, rise 2, run 1. And I keep doing it in both directions until I get these points that are really far away. If I connect the points that are really far away, everything else in the middle is going to fall in line. If I only do it for two that are close together and I connect them, out as you get further away, the lines might not be fully accurate. They might kind of, a slight little variation in where they should be here will become exaggerated out there. So it's better to keep doing the rise and run over and over again to get the points that are furthest away on the graph and connect those, and everything will fall in line. Anyway, then you can see that where it crosses, and you need to be able to be good at identifying coordinates, because if you mess up the coordinates, you might find the right spot where they cross, but if you don't identify the coordinates correctly, you plug them in, they won't work out because they're not the right coordinates, okay? Anyway, let's keep going. All right, so this is a real world application of this, and what it says is that scientists studied the weights of two alligators over a 12-month period. The initial weight and the growth rate is shown below here in this. It's small, but it says alligator 1 had the initial weight of 4 pounds and the growth rate of 1.5 pounds per month. Alligator 2 had an initial weight of 6 pounds, but only had a growth rate of 1 pound per month. Okay, so even though this one is smaller at the start, it's growing faster and it'll eventually catch up. So after how many months did the alligators weigh the same amount? And we assume that the initial starting point is time 0. Okay, so what do? We say, okay, we say the relationship is the alligator's weight is their initial weight plus the growth rate times however much time, or their weight is the initial weight plus the growth rate times time, both times, right? Okay, so those are two equations where time is going to be independent. Their weight depends on how much time has gone by. So time is the independent variable. We put that on the x-axis, okay? Time in months. And this, of course, then is time 0. So that's going to be their initial weights. That's going to be the y-intercept. And you graph the lines. And what you see then is at 4 months, they both weigh 10 pounds. That's where they cross and have equal weight. So graph both equations on the same coordinate plane. The intersection is 4, 10. Notice that the x-coordinate is 4, meaning time in months. So after 4 months, and the y-coordinate is their weight in pounds. After 4 months, both alligators weighed 10 pounds. Okay? You're going to do a problem on the next slide, your got it problem. Okay, so this one is your got it problem. One satellite radio service charges $10 per month plus the activation fee of $20. That means at the start, you're going to have this initial cost of $20. The second service charges $11 per month plus an activation fee of $15. In what month was the cost of the service the same? Okay, set it up as an equation. You can relate C, the cost, to either T, time in months, or M, number of months that have passed. Write the two equations, graph them, find where they cross, and just plug them in to check. You will do that and come back and see the answer. If you don't do it, if you just watch the answer but you don't actually do it, you're not really getting the proper practice. And it's like watching somebody juggle. You're not going to be able to juggle if you're just watching somebody do it. You need to do this practice yourself. So when the video stops, get your graph paper, write the equations, graph them, find the solution, plug them in to see that they actually solve them both. Okay, so let me show you what I did here, and I'm not quite done with the problem because I want to finish it with you. One satellite radio service charges $10 a month plus a $20 activation fee. Here's that one-time activation fee. That's going to be a constant at the end. That's not going to change that amount based on the number of months. What will change based on the number of months is $10 per month. So that becomes the coefficient times the number of months. That's the first equation in red. The second one is $11 per month plus an activation fee of $15. So there is a one-time fee of $15, excuse me, and then every month it increases by 11. So it's the coefficient of M, the number of months. Okay. Now, what did I do with the first one? Well, I said, okay, by the way, I chose the scale as being 5, okay, because this one's going to 20, this one's going to 15. So going by a scale of 5 says, okay, 10, 20, 30, 40, 50, right? Every mark. So every box is 5, 5, 10, 15, 20. That's the first one there. And then I had 1 month being 2 boxes. Okay, so I say I go over 1 month, that increases me by 10. Go another month, increases me by another 10. And I go all the way up and I do that. That's the first line. And if I then said I want to draw it, I could say, okay, how do I make my line? Well, I'm going to go from the points that are furthest apart, and that'll make everything in between fall nicely in line. So there's that. Now, the blue one. The blue one has a y-intercept of 15, meaning 15 at 0 months. That's right here. Okay. Now the bit is my boxes for cost are 5-unit boxes, but this isn't a nice multiple of 5. So what I'm going to do is I'm going to say, what would make a nice unit of 5? What if I went over to 5 months? 11 times 5. So I can go over to 5 months, right? And 11 times 5 is 55, plus this is 70. That'll give me a nice even multiple of 5 to go to. So go to 5 and up to 70. So here's 10, 20, 30, 40, 50, 60, 70. So if I go to 5 and comma 70, I didn't pick that point because it was the solution, although it happens to be, okay? I picked that, what I did there is I just said, I want to make my answer be a nice neat multiple of 5. So I can plug in any number. I can move by the slope, but I can also just say I can find a second point by plugging in a value for M, and it'll produce a number for C, and that'll be a second point somewhere. So I did that by plugging in 5 so that I got a multiple of 5 and 5 comma 70. Turns out that that is the solution. If I graph from there up to there, oops, I graph from there up to there, you see it looks like that. And I can adjust for this graph. I can grab and adjust to make sure that it lands exactly where I want it to land, okay? But you see that they're crossing there at the coordinates of 5 months for time, comma, $70 for the total cost. So what can I do then? I can go back and I can plug those values in to C, which is the total cost, which we determined is 70 for our solution, is equal to 10 times the number of months, which we said that was 5 months. Really, when I say when we said that, is what I mean is that that's where the lines crossed. Okay, and if I then finish solving this out, we get 70 equals 50 plus 20, or 70 equals 70, and that is true. Now we have to check it for the next one. So we say, okay, I'm going to put in the value C of total cost of 70 is equal to 11 times the number of months, which is 5, plus 15. Okay, and then when I solve it out, I get 70 is equal to 55 plus 15, or 70 equals 70, which is true. So that is our solution. After 5 months, both satellite radio services will have cost you $70. Okay, so I'm going to give you some notes here, but I'm going to tell you that as teachers here at CMS, we are less concerned with you getting all of these and quizzing you on these words, but we just want you to hear them and know the terminology, okay? A system of equations that has at least one solution is consistent. Consistent means there's something you can plug into both equations to solve it, okay? Now, when it's consistent, it can either be independent or dependent. Now, a consistent system that is independent, like this, has exactly one solution, okay? It's consistent and it's independent. One is independent of the other. One line is independent of the other, okay? But it's consistent because that means we have a value that solves it. Now, okay, a consistent system that is independent has one solution. The ones we've done already were ones that were like that. A consistent system that is dependent has infinitely many. Red plus blue makes purple. That's why you see purple here. It's basically essentially a combination of the two. They're sitting on top of each other. The lines are exactly the same, so they have an infinite number of solutions, right? Every single point along the line solves both of them because they're the same line, okay? So it's consistent, there's a solution, but it's dependent. One depends on the other. Exactly one is the same as the other. That's what it means by dependent, okay? The other possibility is that there's no solution, it's inconsistent. You say, this is just an inconsistent system. We can't actually find anything that works, okay? Parallel lines are inconsistent. They have the same slope, but they have different intercepts, which means they're separated and they're never going to meet, so they're inconsistent, okay? It's less important that you've got the words consistent and independent and all of that, and more that you understand that if they cross at one point, we've got a single solution. If they never cross, because they're parallel, there's no solution. But if they are describing the same line, and you can have two equations that look different but describe the same line, they would be an infinite number of solutions because any point on one, the coordinates of that will also solve the other one. All right, so what does it look like when you have this situation going on? Let's look at the first one. What is the solution? Use a graph. It might not be clear that what's going on here, so you may need to rewrite this equation, okay? But you can graph them. We've taught you how to plug in 0 for x to find the y-intercept and 0 for y to find the x-intercept, okay? When you graph these, you find that it's exactly the same line. They land exactly in the same place, okay? Any point on the line is the solution of the system. So there's an infinite number of points that are on that line because it's doing both of them at once, okay? The system is consistent, there's a solution, but it's dependent. One is fully dependent. The results, well, when we say it's dependent, meaning if you get one answer here, you're going to get another, that's going to be an answer on the other one. So you can say that if something is a solution to one, it depends. Is it the solution to the other? Yes, then it is. Okay, so they're the exact same equation. Short answer is they're the exact same equation. So all points will solve it. Now, what about this one? Well, look at this one. Okay, if you were to graph these, and here's the graph, okay, you'll see that they're parallel. You can look at this and see that they're parallel. They both have the same slope. Now, if they have the same slope, it might be the same line, but it would also have to have the same intercept, right? Once it's got the same tilt of the line, but it's hitting the y-axis at different places, then they're separated. They're parallel, so there's no solution, and the system is inconsistent. And again, if two equations have the same slope and they also have the same y-intercept, their graphs will be the same. Now you can look up here and say, but these had different equations and they were the same line. Well, if we were to rewrite that, just to do it, you'd say, what if we rewrote 2y minus x equals 2, okay? I'm going to add x to both sides, and we get 2y equals x plus 2. And if we had divided both sides by 2, and I'm kind of writing all over everything, so what if I divided everything by 2? Okay, then I would get y equals, and then remember the number in front of x is 1 if you don't see it, so that's 1 over 2 now, 1 over 2x, or 1/2 x, and 2 divided by 2 is 1. Turns out it is actually the exact same equation. Oops, it is the exact same equation as right there. It just was written in a different way, so it wasn't obvious. But when you graph it, you can see it, that it is. Okay? They've got the same slope, same y-intercept, so it means the same line. Here's your got it problem. What it says here is, what is the solution of each system? Use the graph and then describe the number of solutions. Okay? You will graph these, and by the way, here it says before graphing, can you determine whether the system has one solution or infinitely many solutions or no solutions? So think about that first. See what indicators there are that would tell you before you even graphed it whether it's going to be just two lines that cross in one place, or whether they're the exact same line twice, or whether they're parallel lines. Try that and see what you come up with. Okay, so one thing, what I'm going to do here is I'm going to say, I can see that these two equations have the exact same slope and different intercepts, which means they're going to be parallel lines. I'll graph them for you. I'll graph the first one in red. We go to -3 for x, and then we have a slope of -1. That looks like this, and I'm just going to freehand draw it. You're going to be using a ruler when you graph yours. And then this next one I'll do in blue is the same. It's got a slope of -1, but it actually has a y-intercept of 5 here. Slope of -1 like that. And so when you draw that line, what you get is, oops, parallel lines. Okay, so there's no solution for that one. What about this one? Well, I'm going to graph the first one because that's easy to graph. Y equals 3x minus 3, and I'll graph that in red. Y equals 3x minus 3, so go down here to -3, and then I have a slope of 3, so I rise 3, run 1, like that. Okay, and I graph it. But what about the next one? Well, for me, it's easiest to graph something if I rewrite it into slope-intercept form, and I can see that it says 3y, not y, so I'm going to divide everything by 3. And when I do that, what do I get as an answer? I get y equals 3x minus 3. That's the exact same equation as we had above. So we're graphing the same line twice, so that next line will also have the exact same graph, and so there's infinitely many solutions for this one. Okay, to do these lesson check problems correctly, you're going to need graph paper, you're going to need to graph these equations, see where they cross, identify that point's coordinates, and plug those coordinates into the equations to make sure that they work. And you should run through and answer all of these questions. You should start to look back too on what have you done, what did you do semester 1, and what did you do in unit 5? Did you do the lesson check problems? Did you authentically try these practices? If you didn't and you're scoring poorly, I'm telling you, as a guy with 35 years since I first learned this math, and I've learned all the high math above it, or much of it. You need to be doing this practice if you want to learn this. And that's where you're going wrong. If you're shortcutting it by not doing this work, and then you find that you're having poor results, well, I'm telling you, I have tons of experience. I'm a teacher. I've been doing this for decades. That's where you're going wrong. You're not doing the practice. So do this practice, solve these, then restart the video and check your answers.